Well, look at all the videos we've done so far, all the topics we've done from the scientific method all the way through to gas laws. This one is still processing. So, all that leaves us with in Unit 3 is the final topic, the ideal gas law. Topic 3.08, made possible by Amadeo Avogadro. Shall we begin? Let's. The ideal gas law. The combined gas law can be used if you have a gas that's changing in pressure, volume, or temperature, or all three. So you have a gas that has a certain pressure, temperature, and volume, and you change two of the variables, and you want to predict what the third one is going to be. Okay, not a problem. But what if you just want to find out information of a gas? For example, you know the pressure, volume, and temperature, and you want to know how many molecules there are in the sample. Or you know how many molecules there are and the pressure and the volume, and you want to figure out what temperature that condition is going to be possible at. For that, we need to use the ideal gas law. So if we don't change the gas conditions, we can make use of the law I'm going to show you right now. Now, here's how we derive it. And just for warning, do not drink and derive. Okay? Thank you. Now, Avogadro's hypothesis says that equal volumes of two different gases at the same temperature and pressure will have the same number of molecules. So equal moles of molecules will have equal volume and equal temperature and equal pressure. Everything's equal. Isn't that nice? Pure equality. I wish we had that on planet Earth. Now, the pressure is measured in atmospheres. It's very important to only measure it in atmospheres. So if it's in kilopascals, you're going to want to convert first, and you'll see why in a minute. Volume will be measured in liters. N represents the number of moles of gas molecules. So each mole contains 6.02 times 10 to the 23rd molecules. But so that we don't have to use that big obnoxious number, we're just going to leave it at moles of molecules. And T will be temperature as before in Kelvin. These are the four variables that we are going to make use of. But you'll notice that atmospheres, liters, moles, and kelvins don't exactly give you a way to cancel units out so that both sides of the equal sign have the same units. Well, do you remember Q equals mc delta T? You had joules on one side, and the units on the other side canceled out to make joules. You had mass in grams, and you had temperature change in degrees Celsius. But we had a third factor in there, specific heat. 4.18 joules per gram degree Celsius. It had all of the units of everything else in the formula. It was what was called a proportionality constant. So the proportionality constant for this equation will have to have the units atmospheres, liters, moles, and Kelvin in order for the units to work out. So let's figure out exactly what that universal gas constant will be. We're going to call that R, the universal gas constant, a proportionality constant that contains all four of those units and a number that relates them. Now, P1 V1 over T1 equals P2 V2 over T2. So whatever pressure times volume over temperature is, it's going to come out to be some sort of constant number. And that constant number will be the number of moles of molecules times this universal gas constant. So PV over T equals NR. Okay. Now at STP, 1 mole of ideal gas at 1 atmosphere and 273 Kelvin will occupy a volume of 22.4 liters. This is what's called the molar volume of a gas. 1 mole of any gas at STP will occupy a volume of 22.4 liters. So if we plug that into this equation, by the way, if we divide both sides by N, we get PV over NT equals R. That way we can actually substitute in and find out what this proportionality constant is. So if we plug in 1.00 atmospheres, 22.4 liters divided by 1 mole times 273 Kelvin, when we plug all those numbers in, we get a proportionality constant of 0.0821 atmosphere liters per mole Kelvin. Now, when you write your work out, you're going to want to write all these units out so that you can keep track of them. For the sake of space, I didn't type them out when I'm showing you the example problems, but that's just to save space on this PowerPoint. So let's show you how this works. Let's first of all rearrange the equation to get rid of denominators, because denominators are a whole big pain in the butt. So let's multiply both sides by nt to get rid of the denominators, and we get PV equals nRT, otherwise known as Pivnert. Pivnert, the ideal gas law. So we can use this to find out how many moles of molecules there are in a sample if we know the pressure, volume, and temperature. Or we can find the pressure, volume, and temperature if we know the number of moles of molecules. And R will always be the same, 0.0821. So here's an example. We have a 5-liter sample of gas. If this was in milliliters, you'd have to convert it. Exerts a pressure of 0.500 atmospheres. If this was in kilopascals, you'd have to convert it to atmospheres at 250 Kelvin. If this was in Celsius, you'd have to convert it to Kelvin. How many moles of gas molecules are present? Well, the formula is PV equals nRT. And if we want to solve for N, we divide both sides by RT. So we get N equals PV over RT. And then we just have to substitute in the numbers. So we have 0.500 atmospheres, we have 5.0 liters, R is always 0.0821. You should write the units out, atmosphere liters per mole Kelvin, so that atmospheres and liters and kelvins cancel and leave us with moles. But once we do the math, 0.5 times 5 divided by 0.0821 divided by 250, right? Hit divided by again, so your calculator knows it's in the denominator. Then you'll get your moles. Now, why did I round it off this way? 3 sig figs, 2 sig figs, 3 sig figs, 3 sig figs, 2 sig figs is the lowest number, so I rounded off to 2 sig figs. And that's as simple as it gets. It's a really easy equation to use. Here's another example. A 10-liter cylinder of gas filled with 8.0 moles of gas at 300 Kelvin. What is the pressure exerted by the gas? So in this case, we're trying to solve for pressure. So we divide both sides by volume to get pressure alone. So volume goes down here, P equals nRT over V. We substitute in the numbers. We have 8.0 moles, 0.0821 atmosphere liter per mole Kelvin, 300 kelvins on top, and on the bottom, we put 10.0 liters, which is the volume. And again, I didn't put the units, but you should. Atmospheres, liters, so that liters cancel out, moles, so moles cancel out, Kelvin, so Kelvin cancels out, so that we end up with atmospheres for our final unit. And again, 2 sig figs is the smallest number of sig figs here, so we can't just write 20. We have to pop in a decimal point to show 2 sig figs when we're done with our calculation. That's as simple as it is. You can use this to find any of the variables. Here's another one. We have an 8-liter cylinder of gas that contains 2 moles of molecules at a pressure of 3 atmospheres. What temperature would the gas be at under these conditions? So we're going to rearrange the equation to solve for temperature. Divide both sides by nR, so PV over nR is what T is equal to. Substitute in the numbers, and then you'll get your answer. Now, why didn't I put a decimal point here? 2 sig figs, 2 sig figs, 2 sig figs, 3 sig figs. You can only have 2 sig figs here. So I had to round it off to 150. I think it was 148, and then I rounded it to 150, something like that. Okay, so this is a very useful formula that's really, really easy to use. And that, ladies and gentlemen, is that. That ends this gas laws and phases of matter unit 3. I hope you did well, and I will see you next time for the next unit. The next unit, by the way, is going to start looking at the structure of the atom. Bye.